so we're recording now. So homework 3 got turned in, hopefully, and I will grade that over the next few days and post it with some comments. But any questions up front on the homework?
I have some.
Mm-hmm.
Indirect proofs. I didn't really understand exactly how we were supposed to do those for the questions, so I, gonna lose some points on that, but figured I'd ask now.
So, let's look in the text.
Yeah, I was looking up how they worked, and that you're supposed to, create some sort of
Contradiction.
I should have looked at the
Yeah.
proof there, but create a contradiction or something.
Mm-hmm. Yeah.
But
so. Mm-hmm. So we've done a few of these.
I see. Okay, so we just need to end up with a false somewhere.
Right. And the way we interpret an indirect proof is, suppose this is true, then false is true. Well, that's ridiculous, right? So our conclusion is this must not be true. And so it must be the original thing that was true, the non-negated conclusion.
I see.
Specifically, what I understood when doing the indirect proofs is that you negate the conclusion and you use the conclusion to find a contradiction in the premises and the propositions.
Mm-hmm.
Yeah, I understood what it kind of worked, but I didn't know what kind of conclusion we get. I get that now. You just end up with a statement and then you prove it out to be false. But saying that it contradicts whatnot doesn't really explain what you're supposed to end up with as a conclusion.
Right.
So it should just be a 0.
Mm-hmm.
Okay.
And the mechanics of what's happening here is, let's say we were trying to prove x. So we begin our proof with not x, and we do some stuff, we do some theorem, some magic, whatever, and eventually we come up with false. Okay, what this proof demonstrates is that if we assume not x, we can prove false. So an indirect proof is actually a direct proof of this proposition, that the negation of x implies false. Well, we know from contrapositives that this is equivalent to not false implies not x. All right, we can flip these things around and negate them. And this is equivalent to not f implies x, which is equivalent to, well, the negation of false is true. So this is a direct proof of the fact that true implies x. And we know that true is always true, and so detachment tells us x is true. So this is why this proof proves x. That's kind of the formal mechanics behind it, but usually we present it as just, assume x is false, and we can come up with something absurd, right? A contradiction. And so there must be a problem with this first statement. And since x can't be false, x must be true.
I see. Okay. That thing that you did on the first one, that's contrapositive, right?
Yeah, this is the contrapositive. Mm-hmm.
Okay. I was doing my contrapositives like that as well. But
okay.
The definition of it was saying that x implies f equals not x implies, or not f implies x, not x.
Mm-hmm.
So I didn't know if it worked if only one was a not, but obviously it does.
Yeah, so it's useful sometimes to think of these things as, triangle implies box is equivalent to not box implies triangle. And you can put anything in the box that you want. You can put anything in the triangle that you want. A lot of times it's, just x and y. But, what goes in here could be, X and not Q implies P or T. And as long as we put that in over here, right, this is still the contrapositive of that. And so it's kind of like grouping things in parentheses, but a little more visually separate.
I see.
Statement. The contrapositive.
Sorry, I missed the beginning of that.
Isn't the triangle on your first left side of your equivalent there? Isn't that triangle supposed to be negated?
Yes. Or I can do it over here. Yeah.
Okay.
Thanks. We almost broke logic there.
I had a question about number 6.
Okay.
I really was just wondering, what's the proper way to, or the formal way to set up your not the variables, but like the statements let this phrase equal P, let this phrase equal Q. What's the proper way to do that? I set it above my proof and then started my proof after I had assigned all of the propositions letters, but I wasn't sure if you were supposed to do those statements inside the proof as their own steps.
So are we looking at number 6 in section 3.5?
That was the only number 6 we had.
Okay.
Yeah, so for example, before I started my proof, before I did like step 1, introduce my propositions, above my proof I had 4 statements saying like, let students do well in a discrete mathematics course, that phrase equal P. So I did that outside of my proof. Is that how you're supposed to do it, or are you supposed to do it inside the proof as a step?
Either way, I would probably do it before the proof. So let me put this off on the side and go back to here. So I would probably do something like, let D be the proposition, students do well in discrete math. And remember, don't use equal signs for this.
Oh, then I messed up.
Well, that's okay. I'll know what you meant. But when we get to propositions that involve arithmetic expressions with equal signs, it gets really confusing if you say let P equal N equal Q. So it won't be a problem for this one. But in general, do something like, let this be the proposition, quote. And so, I would do all of those. Let S be the proposition, let C be the proposition, and so on. And then I might restate the problem. Prove D, comma, S, not C implies, Q or something like that. And then go ahead and do your proof using these things. So first I would change it from, the word problem, for this, for that, therefore this, right? Use these definitions and rewrite it into something more symbolic. But I'm not super concerned about if you put the word proof up here or the word proof down there or something like that. Someone said propositions question mark in chat. What's the question there?
The kid who just asked the question, or the dude who just did, was wondering the term.
Oh, okay, got it.
Also, I have a question.
Yeah.
On number 6,
Mm-hmm.
for the proof, there looked like to me 2 things on the left and 1 thing on the right. And one of the things on the left, it was the statement, students who do well go to class. And the thing that we had to prove was students who do well go to class.
Let's see.
I was confused on that. It proves there's nothing to prove. It's already proven.
Well, students who do well in courses do not skip classes, but you're asked to show students who do well in a discrete mathematics course do not skip classes.
Oh, bugger.
So let's write this one out, right? D is the proposition.
I don't understand how.
So D is the proposition students do well in discrete math course. Let's let S be the proposition students study hard. And then I don't know, I'll let C be the proposition students don't skip classes. And let W be the proposition students do well in courses. And the wording on the problem is a little strange because does doing well in a course mean you do well in a discrete math course? And we talked about that last time and suggested doing these as two separate propositions. And it should still come out. So
two separate propositions that still work for me.
Okay. So now we've
the same, which may explain why it was so easy.
Yeah.
Word problems.
So for students to do well in math courses, it's necessary that they study hard. And we broke this one down on Monday also. This is some kind of conditional statement. And the direction of the conditionality here is that if you do well, then you must have studied hard. So it goes in that direction. So to do well in a discrete math class, it's necessary that you study hard. And so if you did well, it's got to be the case that you studied hard. So that was the first big trick, was figuring out is it D implies S or S implies D. So it's necessary that they study hard. Students who do well in courses do not skip. So if you do well, then you do not skip. And if you study hard, which is S, then you do well in courses. And so you're asked to conclude that if you do well in a discrete math class, then you do not skip classes. And this turns out to be one big long chain rule, right? D implies S, S implies W, W implies C. So if you do a series of chain rules, you can show that, D implies S, S implies W, and so D implies W, W implies C, and so D implies C. And that's what you're trying to show. So it does turn out to be true.
Yeah, when I was trying to figure out how to set it up at first, reading the English and turning it into a conditional statement, I almost fell into the trap of thinking about it in terms of cause and effect, and I was getting confused by that, and I had to stop and think, no, that's an English ambiguity.
Yeah, and that's always kind of a challenge with word problems, especially in this subject, is that the English often sounds like cause and effect, right? If I win the lottery, I'll have breakfast in the morning. But I'm not having breakfast because I won the lottery. I'm having breakfast because I wake up and I'm hungry. All right, other questions or things to talk about here? So let's just eyeball homework 4, which I posted a little while ago. Let me bring this up. So homework 4, 6 questions, and I actually posted them here. So they're not questions from the book. First question. I want you to tell me a pair of propositions, P and Q, and use them to give an example of the fallacy of denying the hypothesis. So remember, denying the hypothesis is the following fallacy. If P, then Q, not P, therefore not Q. And this is not a theorem, right? There are cases, there are P's and Q's for which this is true and this is true, but this is not true. So we can find examples of propositions P and Q that clearly illustrate this fallacy. So the goal here is to, define a proposition P and a proposition Q such that this is true, but this is false. And I'd like you to pick propositions that make this clear to anybody reading your argument that, this is true and this is true and this is false. So I'd rather you didn't use propositions like, my cat is a finicky eater, because I don't know if your cat's a finicky eater. And if you come down to a conclusion that says, my cat likes me, I don't know if that's true or not. But if you make a proposition, about the moon is made of green cheese, or the earth is flat, or 2 + 2 = 4, or something like that, propositions where this is true, this is false, that would be a clear demonstration of the fallacy of denying the hypothesis. And then do the same thing. You can use a different set of propositions, if you like, for the fallacy of affirming the conclusion. And remember, affirming the conclusion looks like this. If P, then Q, Q, therefore P. And so you want propositions where this is clearly true, but this is clearly false. So that's part one. It's not a proof problem per se, it's a counterexample. So you come up with a P and Q, you write down what the fallacy says, and then you explain why that's true, that's false. Alright, and then the last 5 problems, these are proof problems. So prove that if n is even, 6n + 4 is also even. And you want to do this using the definition of even or odd for the later problems that we worked with, and the rules of logic, right? So we're going to be talking about modular arithmetic this week, and next week we're going to be talking about, how to tell if something's divisible by 2. You're not allowed to use that here, okay? You got to do this using the rules of logic. In fact, let me edit this. So we'll just hit that one off up front, because we're going to learn some really cool machinery this class and on Monday that would let us answer these questions, in one line. That's not the goal here. Okay, you got to use the propositional logic topics that we've been working with to do these questions. So question 2, if n's even, prove that 6n + 4 is even. So how do you do that? Assume n is an even integer. Write down what that means based on the definition. There exists an integer k such that n = 2 times k. And then try to do something to convince the reader that 6n + 4 is even. Which you can do if you can convince the reader that 6n + 4 can be written as 2 times an integer. Alright, question 3. If n is even, n² + n is even. So we already showed n² is even. So same idea. If n is even, show that n² + n is even. And then prove that if n² is even, n is even. And prove that if n² is odd, n is odd. And we did one of these on Monday. But if you need to use some other facts about evens and odds and squares and stuff, you need to either do those as an earlier problem or as part of this problem. So it will be useful to know that if n is even, n² is even. but you're going to have to prove that as part of your solution. Don't just say we did this in class once, right? Because a lot of these we did in class. So a full proof. Everybody got that?
Yes, sir.
And then question 6 relates to divisibility, which we talked about on Monday, and we're going to work with more today. Prove that assuming all these things are integers. If a divides x and a divides y, a also divides 5x plus 3y. And remember, this is a proposition. In particular, it's a proposition. This is the proposition. A divides n, which is also the proposition there exists some integer such that n equals a times k. So here's a proposition, here's another proposition, here's a third proposition. You're trying to show if those first two propositions are true, the third proposition is true. Alright, so that's homework 4. Alright, we also have a midterm coming up. And so the midterm is a week from today, and Monday we'll spend some time talking about what you can expect to see on the midterm. But the midterm will be very, very similar to the homework questions and the problems we worked out in class. And so going back through the homework is a really good way to prepare for the midterm. And in the textbook, you know, I've been assigning some questions. Mostly I assign even-numbered questions because the odd-numbered questions have answers in the back of the book. So this means, you know, if you worked on question 4 and you kind of got the idea, but you're not quite sure and you want some more practice with it, right? You can go back and you do question 3. And you got more theorems here that you can prove directly and indirectly, and the solutions are available in the text. And my suggestion is, you know, work on these. Don't look at the answers, though, because once you see the answer, you can't figure it out on your own, and you've lost that as a practice problem, right? But you know, work on these, and if you're really, really stuck, you know, maybe leave it and go on to another one. And if you get through, you know, most of them, and there's one or two that you're still just like totally stuck on, then maybe, you know, take a peek at the answer for that one question, and look far enough to see if you can get to, you know, something that gets you past wherever you're stuck, and then finish it up on your own. And you know, use these things carefully because there's only so many of these. But you can make up theorems, you know. You can you know, look through the text and find other examples of this. And at the end of each chapter, right, so we're in chapter 3, which is propositional logic, there's always supplementary questions. Chapter 3 is kind of long. Supplementary exercises. So each section has additional chapters, additional questions. So 3.5, there's some more proof examples. There's some good word questions. Alright, so we'll talk more specifics about the midterm on Monday. But keep looking at your homeworks. It's definitely like your best preparation. All right, Well, let's let's go back to number theory. And we started by talking about divisibility and this idea of, you know, when one integer divides another, meaning the other is a multiple of the first. And I had put forth a theorem and suggested you could try to work on this on your own if you like. Did anybody tackle this one?
I discovered a really good show, and that's all I did.
Ah, okay. That works. I cannot get lined up with the camera. I'm using my USB port that I normally use for my other camera. So we got a strange angle. So how could we prove this? It's similar to what we did before, right? We proved some other theorems involving divisibility. You know, let's start with our hypotheses. A divides B. And then I'll go ahead and write out what that means. So there exists an integer k such that b equals a times k. That's the definition of divisibility. And then I'm going to put down my second hypothesis, b divides c. And I'll explain what that means by saying there exists some possibly different integer j such that c equals b times j. And that's the definition of divisibility. Meanwhile, over here in my ignore section, I'm thinking out loud, and I'm thinking I want to show a divides c, so I want to show c equals a times some integer, right? I'm just thinking out loud here. So how can I show that c is equal to a times some integer? Well, what have I done so far? I've only got, you know, one statement that really like involves c and an equal sign, and that's right here, and I've shown that c is equal to b times an integer. Well, I want to show that c is equal to a times an integer. And I know that c is equal to b times an integer. And if you stare at this and you defocus your eyes a bit and so on, you might eventually see, you know, this b and this b and think substitution. Substitution's always a good go-to when you're trying to do any kind of proof. Substitute. A lot of times that's the whole key. So let's just substitute this expression for b into here. And let's say c equals a times k times j. And that's just substituting statement 2 into statement 4. And now if I'm still looking at my ignore section, what have I got? I've got c equals, well, this looks pretty close to a times an integer. That's just algebra. That's the associative property of multiplication. And then I have to use the fact that when you multiply two integers, you get an integer. So k times j is an integer. That's the closure property of multiplying integers. And I'm done. Well, I can't say QED yet, but the hard work is done. I've shown that c can be written as a times an integer. Well, if I can write c as a times an integer, that's equivalent to saying a divides c. That's the definition of divides, together with what I showed in statement 6 and statement 7. And that's the end of the proof. And so your last homework question for homework 4 on divisibility, very similar feel to what we're doing here. Different specifics, but same basic idea. Write down your hypotheses. If they involve divisibility, spell out what they mean. Don't confuse, you know, don't put a J down here because I can't say C equals B times K if I already said B equals A times K. Because now I'm stating something that's not necessarily true. And then, you know, think about what you're trying to show, look at what you've got written already, and see if you can do something legal with those to end up with what you want. And then put it together in a formal way.
For number 6, does it say K times J, or is that K plus J?
That's a K times J.
Okay, thank you.
Yeah. So the ability to prove these things is underneath a lot of what we're going to do. But a lot of what we're going to do in this part of the course is using properties related to divisibility rather than just proving, you know, if A divides B and B divides C, A divides C. We want to be able to make some statements about what happens when we divide things. And so there's a theorem that's not actually a theorem as much as an operation. So this theorem is called the division algorithm. And maybe it's an algorithm, maybe it's a theorem. It's a kind of unfortunate naming. Alright, so what is the division algorithm? So let A be any integer. And we're going to call this A the dividend. And let B be a positive integer. So it's an integer bigger than 0. And we're going to call this the divisor. So we're going to do something related to taking A and dividing by B, right? When you have A divided by B, A is called the dividend, B is called the divisor. So throughout this, think about, you know, A divided by B. All right, so I'm going to put down the formal definition of this first, and then we'll talk about what it actually means in, like, plain English. So let A be any integer, let B be a positive integer. There exists a unique integer Q and an integer R, and I'm going to call Q the quotient, and I'm going to call R the remainder. So there exists a unique pair of integers, the quotient and the remainder, such that the remainder is between 0 and d minus 1, and A is equal to d times Q plus R. Alright, so this is probably not terribly inspirational. But this is the formal definition of the division algorithm. Given an integer A and a positive integer B, there's a unique pair of integers, a quotient and a remainder, such that A can be written as something times our quotient. Sorry, this should be a B. Let me call this D for divisor. So dividend and a divisor. So there exists a unique pair of integers Q and R such that A, our dividend, can be written as our divisor times Q plus R. and with the property that r is between 0 and d minus 1. Okay, so what does this mean? Example. Let a equals 17 and d equals 3. This theorem is saying that we can write 17 as something times 3 plus something else. Right, we're going to call this q and we're going to call this r. And we can write it uniquely in this way such that 0 is less than or equal to r is less than 3.
5 times 3 plus 1. Or plus 2. No, yeah, plus 2.
Say again?
5 times 3 plus 2.
17 equals 5 times 3 plus 2. So we've written 17 as an integer times 3 plus another integer that is bigger than or equal to 0 and less than 3. And the theorem says there's a unique way to do that. Now I can write 17 in this form a number of ways. I could write 17 equals 4 times 3 plus 5. But in this case my r5 would be too big. I could write 17 equals 6 times 3 plus negative 1. And that's true, but in this case, this number here, my r, would be too small. It's not bigger than or equal to 0. But there is a way to write 17 as something times 3 plus something where this is bigger than or equal to 0 and less than 3. And there's exactly one way to do that. That's what the division algorithm says. And this works in all kinds of cases. So for example, if I wanted to do 2 equals something times 11 plus some remainder, where here the remainder is bigger than or equal to 0 and less than 11. So can I do that? Can I find values for q and r that satisfy this?
Why is it times 11? Wasn't it? What was it times before?
So d times q plus r.
Oh, d. Right. Oh, okay.
Yeah. So can I find values for q and r that satisfy this?
Yeah, 0 and 2.
Yeah, 0 and 2. How about this? Negative 5 equals something times 3 plus something, where this something's between 0 and 2.
Negative 2 and 1.
Right, so negative 5 is negative 2 times 3, that's negative 6 plus 1. And again, just this part of it, it's not a unique solution. I could write this as negative 1 times 3 plus negative 2. I could write it as negative 3 times 3 plus 4. Or, sorry, plus 4. But of all the different ways I can write it, only one of these will satisfy this condition as well. So there's a unique way to write a as a multiple of q plus some remainder. All right, so we're not going to use this theorem a lot directly, and we're not going to prove it. Proving it is pretty hairy. But this theorem underpins what we're going to do, which is modular arithmetic. So here's a definition. So we're going to write this A triple equal sign B parentheses mod M. And if we want to say this out loud, we're going to say A is congruent to B modulo M. So this triple equal sign here means congruent to. A is congruent to B modulo M. So this means M divides A minus B. That's the definition of this congruent symbol. So when we say A is congruent to B mod M, all we're saying is M divides the difference of A and B. So for example, 17 is congruent to 14 modulo 3. Why? Because the difference of these two numbers is 3, and 3 divides 3. 17 is congruent to 11 mod 3. Why? Because their difference is 6, and 3 divides 6. (17) is also congruent to minus 1 modulo 3. Why? Because 17 and minus 1, the difference between those numbers is 18, and 3 divides 18. And we can also write something like 17 is not congruent to 15 modulo 3. Because the difference of these numbers is 2, and 3 does not divide 2. Alright, everybody good on this definition?
So that can always be true?
Is what can always be true? This definition?
Yeah.
Yeah.
Sure, okay.
Yeah, anytime we write this, it's going to guarantee this. And anytime that this is true, we can write that.
Thank you.
The formatting on this is fairly strange.
Yeah, it is. Well, we'll do it a bunch, so we'll get about a bunch of practice with it. Alright, well, we said 17 is congruent to 14. Guess what? 14 is also congruent to 17. Why? Because the difference between 14 and 17 is negative 3, and 3 divides negative 3. It's 3 times minus 1. And 17 is congruent to 11 because 17 minus 11 is 6, which is a multiple of 3. Well, by the same token, 11 is congruent to 17 modulo 3 because 11 minus 17 is negative 6. And negative 6 is also a multiple of 3. It's 3 times minus 2. And just to push the point a little further, minus 1 is congruent to 17. Because minus 1 minus 17 is minus 18, and that's minus 6 times 3. 3 divides minus 18, so these are congruent. And so you can probably see the generalization of this. If A is congruent to B modulo M, we said that means M divides A minus B. So M divides A minus B. So A minus B equals some integer times M. And so we can multiply both sides by minus 1 and see that b minus 1 equals minus k times m. And if k is an integer, which it is, then minus k is also an integer. That's just a property of integers. And since b minus a is m times some integer, we can say m divides b minus a. And if m divides b minus a, that means b is congruent to a modulo m. So this congruence business is commutative. If a is congruent to b, b is congruent to a. So it's commutative. Can you prove that for any integer a is congruent to itself modulo m? Is that a hard thing to show?
What's this m? Is it just any number?
Any positive integer.
Okay.
So what do you think? Is every number congruent to itself?
I want to say yes.
Yeah, say it. How could we show that? What does it mean if we say a is congruent to a? What does our definition may say?
I don't know. I just know that a minus a would be 0.
Yeah.
So there would
So this
be a
says
split.
m divides a minus a, which is the same as m divides 0. Well, it turns out every positive integer divides 0. If I want to show a is congruent to a mod 17, well, I know that 0 equals 17 times 0. So 17 divides 0. So 17 divides a minus a. So congruence is commutative. It's also what we call reflexive, which just says a is always congruent to a. And it also turns out if a is congruent to b and b is congruent to c, then a is congruent to c. And we're working under some unstated modulo m here. Well, how could we prove this? If a is congruent to b, this means m divides b minus a. And b is congruent to c, so that means m divides b minus c. And this is just some algebraic gymnastics. So if we know m divides b minus a, that means b minus a equals m times some integer, which I'll call k1. And if m divides b minus c, then b minus c is equal to m times some other integer k2. And so if I do b minus c minus b minus a, that's equal to m times k2 minus m times k1, right? Because b minus c is m times k2, b minus a is m times k1, and this is just m times k2 minus k1. So just kind of working with the definitions, we could see that m divides this. But if you do the algebra and expand this, your b's will cancel each other. And it'll just end up with minus a is a, minus c, plus b minus b. M divides a minus c. And if m divides a minus c, then a is congruent to c modulo m. That's a fun proof to work through because it's really just working with the definitions, but it's a good way to familiarize yourself. So this is what we call transitive. If a is congruent to b and b is congruent to c, then a is congruent to c. Properties that relate elements to each other that satisfy these three characteristics are extremely powerful. It's a particular type of relationship that we call an equivalence relation. And there's all kinds of things that we get for free once we know that a relation satisfies these three properties. If you do a course in abstract algebra, you'll dig deep into equivalence relations and some really powerful machinery around that. But we're just gonna take comfort in these properties of congruence modulo m. But I want to point out that this looks a lot like plain old equality of numbers. If we just think of a double equal sign comparing integers, well, if a equals b, b equals a, we know that. And every number is equal to itself, we know that. And if a equals b and b equals c, a equals c, we know that too. And so a plain old double equal sign is an example of an equivalence relation. And this congruence satisfies those same properties. And not surprisingly, a lot of what we're used to doing with equal signs will work just as well for this congruence operation. And this is where all sorts of good stuff is going to come from. So let me mention a few other facts about congruence, and I'm not going to prove these, but you could prove them using the same kind of ideas that we used to show some of these other characteristics, but mostly by working with the definitions, right? So here's some other theorems, and I'm just going to fix modulo m. I'm not going to keep writing modulo m next to each of these statements, but everything we're doing here is just think of some fixed positive integer m. We're working in that modulo. So here's a theorem. If a is congruent to b and c is congruent to d, then a plus c is congruent to b plus d. So you can kind of line these up and add them together. If a is congruent to b, a plus 1 is congruent to b plus 1. A plus 2 is congruent to b plus 2. A plus 1,436 is congruent to b plus 1,436, and so on. I can add a fixed number to both sides, and I preserve the congruence. I can also multiply. I can say that 2 times a is congruent to 2 times b. Or 15 times a is congruent to 15 times b. Or negative 1,001 times a is congruent to negative 1,001 times b. So I can multiply both sides by a fixed integer, and the congruence is preserved. I'll also get a squared is congruent to b squared. I can take the square of both sides and preserve congruence. And if I can do that, I can do a cubed is congruent to b cubed, a to the 97th is congruent to b to the 97th, and so on. So this congruence operator works kind of intuitively. A lot of the things that we would sort of like this thing to do if it were a plain old equal sign actually work for congruence. And that makes working in these modular systems pretty familiar, even if this is a new concept to us. The intuition we've developed from doing algebra and equality and, you know, algebraic manipulations, a lot of that intuition will carry over faithfully to working with modular systems, working with congruence. So some examples of that. (23) is congruent to 3 modulo 5. Right? In other words, the difference between 23 and 3 is 20. That's a multiple of 5. If I multiply both sides by 2, I should find that 46 is congruent to 6. Which it is. The difference between those is 40. That's also a multiple of 5. If I add some quantity or subtract some quantity from both sides, let's say I subtract 2 from both sides, I should find 21 is congruent to 1, which it is, because their difference is 20, which is a multiple of 5. And if you think about it, what happens when I add some constant to both sides? If I know 23 is congruent to 3, I'm guaranteed this is congruent to this. Why? Because the difference between this and this is exactly the same as the difference between that and that. If I add k to both sides, I'm not changing the difference when I subtract. So if I know the difference of these is a multiple of 5, I don't even have to think about it. I know the difference of these is also a multiple of 5. And so we could work up, you know, formal proofs of all of these things. All right, let's do a 5-minute break. We'll come back. We'll keep going with this. I fixed the clock. Did you notice? It chimed twice.
Oh no, I didn't notice.
Magic.
That's great. Thank you.
I just spun the hour hand up and out, or the minute hand up 60 minutes.
Yeah, that makes
Push the
sense.
hour hand back.
Yeah. That's like the thing I kept meaning to do.
Yeah. I did it a bunch of times in my sleep last night.
Oh no.
I better do it before I go to sleep.
Yeah.
Was that a rapid test?
Uh-huh.
They're gonna call you or something?
Yeah. one in the fridge? Did you, I've been trying to keep 2 in there for both of you. Did you go to the mailbox yesterday?
No.
Because it was empty when we stopped, so.
There was one thing listed on the dashboard.
Ah, okay.
Did not look too exciting.
Yeah.
Contagion cup, so avoid that. Alright, we're back. I'm going to send out an announcement later through Canvas about this, but I was told a little while ago that regarding COVID-19 vaccination, so students have been required to attest to either having been vaccinated or having a approved exemption. And along with that attestation, there was supposed to be documentation provided by the student in the form of uploading a scan of your vaccination card or the paperwork for an exemption and so on and so forth. And apparently the system that was supposed to check all of that had a glitch, and there's about 1,500 students at Clark who did not upload their documentation but were still allowed to remain enrolled in classes. So this glitch has been discovered and presumably corrected. And so if you did your attestation but did not upload your documentation, you need to upload the appropriate documentation by Friday at 5. Otherwise you get dropped from all of your in-person classes, and this is one of the in-person classes. Even though we've been remote, we still might switch back to in-person at some point. So yeah, if you have not done that, the school is in the process of trying to reach you through emails, phones, and texts. But if you don't have up-to-date contact information in CTC Link and such, it's possible that those won't reach you, and you don't want to end up getting dropped from the course. So, but if that happens, send me an email and we'll work through the process from there.
I was kind of wondering about that because on Canvas they did give you like a option to fill out time and dates of when you got vaccinated, but they didn't have you plug in like an actual scan of anything.
Okay.
And I did get an email and I just sent them a scan.
Oh, okay. So maybe the mistake was earlier in the process of not requesting.
Through CTC Link, you mean?
Yeah, CTC.
Yeah.
Okay.
Okay, yeah, so definitely make sure you do that and pass that on to others who aren't here. And I'm planning to put an announcement on Canvas later on today for all my classes, along with a notice involving certification of enrollment for people who are getting veterans benefits They've changed the requirements, and they require monthly recertification of your enrollment in classes, and the VA office hasn't been able to reach all of the students, so I'm going to put that note in an announcement also. So you'll see a couple of announcements coming through later today for all of my classes. All right. So continuing with modular things. So what we're working up to with this is the idea that the division algorithm actually gives us something else, right? So we have this notion, you know, A congruent to B mod M means A divides, or M divides A minus B. And we have this division algorithm which says that we can write, you know, A as, you know, M times something plus something else, where this thing is between 0 and M minus 1. And so what we can do is let's fix a modulo. Let's pretend m's equal to 3, so we're just going to work modulo 3, right? Looking for when the difference of two things is divisible by 3. And we've seen some examples, right? 17 is congruent to 2. 17 is congruent to 5. 17 is congruent to 8. The difference of each of these is divisible by 3. 17 is also congruent to minus 1, and so on. But the division algorithm basically tells us that if we write down all the numbers that are congruent to 17, there's exactly one of them that sits between 0 and m minus 1, 2 in this case. And so for any number, there exists a unique integer r between 0 and 3, exclusive of 3, such that n is congruent to r modulo 3. So if we fix our modulo at 3, right, we're just thinking about mod 3, for any number n that you pick, I can find some number, 0, 1, or 2, that n is congruent to. In other words, if I'm working modulo 3, every number can be written as being congruent to either 0, 1, or 2. Alright, that's what the division algorithm tells us. And all of this other business about equivalence relations and reflexive relations and commutativity tells us that basically we can do arithmetic on these equivalences and make statements about doing the same arithmetic on the original numbers. So for example, let's just work mod 3. What is 17 squared congruent to modulo 3? Well, I can take 17, I can multiply it by 17, I can get 289, and I can divide that by 3 and see what the remainder is. And that will tell me what 17 squared is congruent to. But I can also do the following. I can say 17 is congruent to minus 1, and so 17 squared is congruent to minus 1 squared. And minus 1 squared is just 1. So I'm guaranteed 17 squared minus 1 will be divisible by 3.
What was that?
Right? And 289 minus 1 divided by 3 is 96. So
I'm confused. You set that that triple equal, I don't know. What's that triple equal?
Congruent.
Okay.
I'm a little confused too. How is 17 congruent to negative 1?
17 is congruent to negative 1 because 17 minus negative 1 is divisible by 3. 17 minus negative 1 is 18.
3. Okay.
17 is also congruent to 2 because 17 minus 2 is divisible by 3. So I could also have said, 17 is congruent to 2. 17 squared is congruent to 2 squared. 2 squared is 4. And so 17 squared minus 4 should also be divisible by 3. Well, I also know that 4 is congruent to 1 because 4 minus 1 is a multiple of 3. And since I have transitivity, 17 squared is congruent to 4. That's also congruent to 1. If I wanted to know 17 to the 200th, well, that's 17 squared raised to the 100ths, which would just be congruent to 1 to the 100th, which is just 1. So if I multiply 17 times itself 200 times, and I subtract 1, I should get a multiple of 3. Well, there's 17 to the 200ths. There's 17 to the 200ths minus 1. And if I divide it by 3, I get an integer. It's a big integer, but it's an integer. But this is a fair bit less work than, multiplying 17 by itself 200 times. So modular arithmetic is going to give us a way to make statements about the results of very complex operations by doing very simple operations. And this is something that's going to be really useful, for example, if we wanted to make a crypto system. And a lot of what we do with cryptography is based on working with really large prime numbers. Think, prime numbers with 500 digits. And to use those prime numbers to encrypt messages, we need to, do lots of multiplications and exponentiations and things like that. And taking a number with 500 digits and squaring it, it's a lot of work. But if we can work in some modular system where that number is congruent to something smaller, we can work on those smaller things and be saying things about the bigger things. So that's our basic storyline here. And the last thing I want to just mention on this before we start digging into more properties is the idea of remainders. So we've said a few times 17 is congruent to 2 modulo 3. It means 3 divides the difference of 17 and 2. But there's another way to interpret this. If I take 17 and I divide by 3, what do I get? Well, if I'm a calculator, I get 5.66667. But if we don't know about decimals, how do we write this in elementary school? We say this is 5 with a remainder of 2. Okay, that remainder right there, that's this 2. And so if I say, 45 divided by 7, what would my answer be in elementary school? Well, 7 goes into 45 6 times with a remainder of 3. This is exactly the same fact as this. .45 is congruent to 3 modulo 7. So when we write a number as congruent to some other number modulo 7, we're also saying that 7, divides the difference of those two numbers, but we're also saying if we just divide that first number by 7, we get this much left over. Which is the same thing as saying if we take that much off of this, now it's a multiple of 7. That's what a remainder is. It's the stuff that's left over that didn't divide out. So if we were to subtract that remainder from here, we should get something that divides evenly by 7. And so here's the other way to think about the division algorithm. Put yourself back in elementary school, and you're doing divide problems, and your teacher wants you to divide 45 by 7. And the answer the teacher is looking for is 6 with a remainder of 3. But it would technically be correct to say this. 45 divided by 7 is 5 with a remainder of 10. It's true. 7 goes into here 5 times, and you've got 10 stuff left over. 5 times 7 is 35, and you got an extra 10. But if you write this, your teacher gives you the frowny face on your paper. And if you're really alternative, you could say 45 divided by 7 equals 4, or equals 7 with a remainder of negative 4. Because 7 times 7 is 49, and it's got negative 4 left over. And this gets you, I don't know, some other face. Right? And this is the answer that gets you the happy face and the points. Right? So what is it about this answer that makes it the correct answer, and what is it about these that make them the wrong answer? The difference is the remainder is supposed to be between 0 and 6. And maybe that's explicitly spelled out, maybe it's just supposed to be understood. But what do you get when you divide 45 by 7? How much do you have left over? The most reasonable answer probably is 3, right? Not 10, not negative 4. If you're a smart Alec, you could say it goes in 0 times with 45 left over, ha ha ha, right? And then you get taken to the principal's office or something. So all of these are technically valid answers, but there's one that's more valid than the others. That's what the division algorithm is telling us. There's a best answer, and it's best in the sense that this remainder is bigger than or equal to 0 and less than 7.
Hello. Hi.
All right, so there's multiple things going on here that we can have in mind when we're working with this congruence symbol. There's this divides the difference of those. There's the remainder when you divide this by this. There's the unique number that satisfies that funny expression of the division algorithm, and so on. And those are all equivalent to one another, but let's not get bogged down on the differences between those. Let's just kind of work with this. Yeah, question, comment?
Is that 0 less than or equal to and less than 7?
So whatever it is, whatever your remainder is, your answer bigger than or equal to 0 and less than 7.
Gotcha. Okay.
Yeah, I was missing the middle part. All right, so let's talk about doing arithmetic in a modular system. And here's an example. There's a clock face. This was how I learned modular arithmetic. And let's say it's 1 o'clock. So we're just going to represent that with the number 1. So if you want to know what time will it be in 5 hours, do 1 plus 5 equals 6. It's going to be 6 o'clock. What time will it be in 10 hours? It's going to be 11 o'clock. But what time will it be in 21 hours? Good? All right. What time will it be in 21 hours? Well, 1 plus 21 is 22. Is it going to be 22 o'clock?
It's going to be 10.
It's going to be 10. So how can we calculate that? We can reduce modulo 12. It will be 22 o'clock in some, version of that universe. But 22 is also congruent to 10 modulo 12. It's actually going to be pointing at the 10 in 21 hours. And all that's happening is that, you start from here and you go around, but once you've gone around 12 times, you come back to where you started. And so you could say, what time is it going to be in 1,000 hours? Well, it's not going to be 1,001 o'clock. It's going to be whatever the remainder is when you divide 1,001 by 12. That many hours past, high noon. And the clock's not a perfect example. The 12 kind of breaks it. That should really be a 0 to make this a perfect example. But that's just a kind of working analogy. Alright, so that's what's happening when we add modular. Basically, every time we get up here, we just roll back over. And so we can do things like make an addition table. So let's work modulo 5. And let's write down what we get when we add two numbers modulo 5. Well, I'll do the first row. 0 plus each of these is just this. What's going to go in the second row?
One, two, four. 1, 2, 3, 4, 5.
Alright, so 1, 2, 3, 4. And then 1 plus 4 would be a 5, but I don't want to put any 5s in here. I want everything between 0 and 4. But what is 5 congruent to modulo 5? So what can I find that's congruent to 5 but between 0 and less than 5? Zilch, someone said. So this is actually a 0. And then 2 plus 0 is 2, 3, 4. 2 plus 3 is 5, which is congruent to 0. 2 plus 4 is 6, and 6 is congruent to 1. 3 plus 4 will be 7. 7 is congruent to 2. And 4 plus 4 is 8, and 8 is congruent to 3. So there's an addition table for numbers modulo 5. And guess what? This is a complete addition table. Because if I'm working mod 5 and I'm thinking about these numbers that I get from the division algorithm, these remainders that are always bigger than or equal to 0 and less than 5, there's only 5 possible numbers. So if I tell you how to add any of these 5 numbers to any of these 5 numbers, that's all you ever need to know about addition modulo 5. You don't need to know what 6 plus 6 is, because 6 is congruent to 1. So 6 plus 6 is congruent to 1 plus 1, and 1 plus 1 is 2. And if I do the hard work of doing 6 plus 6 and I get 12, right, I can easily see 12 is congruent to 2 mod 5. Because 12 minus 2 is 10. It's a multiple of 5. And there's symmetry about this axis. 1, 2, 3, 4, 1, 2, 3, 4, 3, 4, 0, 3, 4, 0. That's your commutativity. A plus B is congruent to B plus A. So addition is commutative. There's a 0 element. 0 plus anything just gives us back that anything. And anything plus 0 gives us that anything. So there's a 0. And there's one other property that's really useful, and that's called inverses. And for any number, there's something I can add to that number that gets me back to 0. For a 3, I can add a 2, that gets me back to 0. For a 2, I can add a 3. For a 4, I can add a 1. For a 0, I can add a 0. And these are called additive inverses. And what's an additive inverse? It's just the negative of a number. In plain old arithmetic, what's the additive inverse of 5? It's what we call negative 5. And when you add those together, you get 0. What's the additive inverse of 11,000? It's negative 11,000. Because if you add those together, you get 0. So we can think of negative numbers. This is tied into 2's complement, by the way. Same idea. We define the negative of something as the thing that when you add to the original something, you end up with 0. And yeah, this is a different type of algebra, basically. It's similar to the algebra that we know and love from, you know, plain old algebra, but it's different in some ways. And let me show you one very peculiar way in which it's different. Let's make a multiplication table. And I'm not going to put in the zeros because I know 0 times anything is 0, and those are kind of not so interesting. But let's make a multiplication table for all the other numbers between 0 and 4. So if I multiply by 1, I'll just get my numbers. What goes in the second row? Let's start filling these in. So 2 times 1. Someone grab the easier ones because they're going to get harder. 2 times 1 is
2.
2, thank you. 2 times 2.
4.
Alright, we're out of the easy ones. 2 times 3.
6, which is congruent to 1.
6, which is congruent to 1. Excellent. And then 2 times 4.
8, which is congruent to, oh boy, 2? No, 3? No.
I should write this down.
I still don't understand congruency perfectly.
Okay, so 8 is equal to something times 5 plus something. This is what it's congruent to 2. So it's equal to 1 times 5 plus 3. So 8 is congruent to 3.
I see. Okay, that makes sense.
The other option is, you know, 8 equals 8 divided by 5 equals 1 with a remainder of 3. Alright, I'll do the third one. 3 times 1 is 3. 3 times 2 is 6, which is 1. 3 times 3 is 9, which is 4. 3 times 4 is 12, which is 2. What about the last row? 4 times 1.
4.
Good. 4 times 2.
8, 3.
8, which is congruent to 3. 4 times 3.
2.
12, which is congruent to 2. And last one, 4 times 4.
1.
1, because it's 16, which is congruent to 1. So there's the whole multiplication table for the world of modulo 5. And we have an identity. We had an additive identity, 0, that, you know, you add 0 to anything and it doesn't change that anything. We have a multiplicative identity, which is 1. 1 times anything is just, what we started with. Anything times 1 is just what we started with. So there's a multiplicative identity. And there's also multiplicative. It's a ridiculous number of syllables for one word. Multiplicative inverses for each number. For example, for 2, there's something I can multiply 2 by that gives me a 1. In this case, 3. There's something I can multiply 4 by that gives me a 1. In this case, 4. There's something I can multiply 1 by, which is a 1, and something I can multiply 3 by, which is 2. So just like with matrices, we don't really define division of numbers in a modular system, but sometimes we can define inverses. Something that you can multiply by in order to end up with 1. Just like we can define a minus as something that you add to a number to get you to 0. Alright, so this is multiplication mod 5. Let me do multiplication mod 6. Bless you. Alright, so let's do multiplication. So multiplication by 1 is pretty straightforward. Multiplication by 2, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, which is 0, because 6 is congruent to 0. We switch to mod 6 here. 2 times 4 is 8, that's 2 more than 6. 2 times 5 is 10, that's 4 more than 6. And I can fill in the columns as I fill in the rows because it's commutative. 3 times 3 is 9, that's 3 more than a multiple of 6. 3 times 4 is 12, that has no remainder when you divide by 6. 3 times 5 is 15, 15 divided by 6, you have 3 left over. 4 times 4 is 16, that's 4 more than 12. And 4 times 5 is 20, that's 2 more than 18. And finally 5 times 5 is 25, and 25 is 1 more than 24, so that's a 1. Alright, here's the $1,000,000 question. What's the most startling difference between this table and that table? It's a subjective question.
One doesn't have zeros.
There are zeros over here, there are no zeros over here. This 0 tells us something fairly surprising.
Anything mod 5 doesn't have 0 over it?
Any multiplication of 2 non-zero numbers mod 5 gives us something non-zero. But here we've got 2 numbers that are different from 0. We multiply them, we end up with 0. This is weird. We don't like this. Well, we do.
It's because it's even, right? Or just a number which multiplies to a lot of...
Yeah, something like that. This breaks a lot of algebra. Think about solving equations in algebra. You're trying to find, something equals to 0, and you end up with, x plus 2 times x minus 1 equals 0. And what do you do from there? You say x plus 2 equals 0, or x minus 1 equals 0. And this tells you x equals minus 2, or x equals 1. Well, how do we know this is true given this? We know it because under plain old algebra, if you multiply 2 things and end up with 0, one of those has to be 0. All of a sudden, that's not the case. We've got 2 things that are decidedly not 0, but when we multiply them, we get a 0. And so working in modulo 6 feels very different from doing plain old arithmetic, from doing things over like the set of all integers where we're used to ideas like this. The other thing to note is that, you know, every row and every column over here contains a 1. Mod 6, some of the rows and some of the columns contain a 1, but some of them don't. There's nothing in this second row that's a 1. Put differently, there's nothing I can multiply 2 by that gives me 1. So there's no multiplicative inverse for 2. There's no number I can multiply by 2 to get 1. Over here, everything had a multiplicative inverse. If I wanted to get 1 from 2, I could multiply it by 3. 2 times 3 is equal to 1. I don't have those inverses over here. So two very different situations. One for modulo 6, one for modulo 5. So when are we going to get this situation versus that situation? What is it about 5 and 6 that foretells this difference in what our multiplication table looks like? Any guesses?
Prime numbers.
Prime numbers. So it's not just even and odd, it's the fact that 5 is prime and 6 is not. And it turns out if we work modulo a prime number, we have this nice behavior where every row and every column has a 1 and no rows or columns contain a 0. And if we work modular a non-prime number, a composite number, we are going to find rows and columns that contain zeros and don't contain 1s. And that's one way that prime numbers link into all of this stuff. Alright, so what can we do with this? As I said, sometimes we want to work with very large numbers and we don't want to do a lot of work. And knowing a few tricks in modular arithmetic make it possible to make statements about very large numbers without having to actually work with very large numbers. And so, for example, what is 3 to the 17th congruent to modulo 7? I shouldn't say what is. I should just say 3 to the 17th is congruent to what modulo 7? So we can multiply 3 by itself 17 times, right? And that's not a lot of fun. So there's a technique called modular exponentiation. And this is a very particular technique. If you Google modular exponentiation, you'll find much more general techniques that are called the same thing. But when I ask you on a homework or an exam to calculate something using modular exponentiation, this is the technique I'm talking about. Okay, and this is the technique that works really well if you want to teach a computer to do this, which is what we do when we make crypto systems. So here's how this works. And this is based on the observation that, you know, if we take the number 17 as a decimal number, we can write it in binary like this. And what is this binary representation all about? It's basically saying that 17 equals 2 to the 4th. That's what this weight of this position is, plus nothing times 2 cubed, nothing times 2 squared, nothing times 2 to the 1st, plus 2 to the 0. Alright, or if you like, it's just 16 plus 1. So we do the following small set of calculations. We say 3 to the 1st, well, it's just congruent to 3. And this is all modulo 7. I won't keep writing that. 3 to the 1st is just 3. If we square both sides, 3 squared will be the square of this side, and 3 squared is 9, and what is 9 congruent to modulo 7? What do you get when you divide 9 by 7?
Kind of like 1 maybe.
9/7 gives you about 1. You got a little bit left over. How much do you have left over?
2.2.
2. Remainder 2. That's what 9's congruent to. So the congruence is just the stuff that's left over when you do the division. Alright, 3 squared is congruent to 2. Do I want to do this another 15 times? No. So I'm going to square both sides. 3 squared squared will be congruent to 2 squared. Square this side, square that side. Well, what is 3 squared squared? That's 3 to the 4th. What is 2 squared? That's 4. Alright, so I know what 3 to the 1st is, I know what 3 to the 2nd is, and I know what 3 to the 4th is. I'm going to do one more operation, and I'm going to jump all the way up to 3 to the 8th. So 3 to the 4th squared will be congruent to 4 squared. 3 to the 4th squared, this is 3 to the 8th. 4 squared is 16. And what is 16 congruent to mod 7? What's the remainder when you divide 16 by 7?
2.
2. So now we know what 3 to the 8th is. And I'm going to do one more of these operations, and I'm going to square both sides and say 3 to the 16th is congruent to 2 squared, which is 4. Alright, what I'm interested in is finding 3 to the 17th. Well, 17 is just 16 plus 1. And law of exponents says 3 to the a plus b is just 3 to the a times 3 to the b. So this I could use single equal signs for, right? 3 to the 17th is guaranteed to be 3 to the 16th plus 1, which is guaranteed to be 3 to the 16th times 3 to the 1. And now I'm actually going to use the congruence. I know 3 to the 16th is congruent to 4. 3 to the 1st is congruent to 3. So 3 to the 17th should be congruent to 4 times 3, which is congruent to 12. And what's the remainder when you divide 12 by 7? That's just 5. So 3 to the 17th is congruent to 5. And I did not have to do 17 multiplications. I did 4 multiplications, and the numbers I was working with were never bigger than 6, which means the largest square I ever had to deal with was 36. And I keep reducing modulo 7 as I go, so the numbers I'm working with on this page are all going to be small. So BC is a binary calculator program in Unix. If I say BC-L, it'll do decimals. And it'll also do really big numbers. So I can do 3 to the 17th, and I get this big number. And I can do that thing minus 5, and I get this number. And I can do that thing divided by 7, and I get an integer. So this number and 5, their difference is divisible by 7. That's why this number and 5 are congruent to each other. But we didn't have to do all the work that the machine did in doing that calculation. We just did this modular exponentiation technique. And that brought us up to 3 to the 17th without too much work. And so we can teach a computer to do this really easily. Why? Because computers are really good at expressing things in binary. And if we can take a number, an exponent here, and write it in binary, we can interpret that as, you know, a sum of powers of 2. And then we simply find 3 raised to each of the consecutive powers of 2, 3 to the 1, the 2, the 4, the 8, the 16. and then whichever powers add up to our exponent, we multiply those powers together. And if you're doing this by hand, and if you're doing crypto on a desert island, you'll be doing it by hand, and we wanted to know, say, 3 to the 31st, right? Well, it's 3 to, 1 plus 2 plus 4 plus 8 plus 16, which is congruent to 3 to the 1st times 3 squared times 3 to the 4th times 3 to the 8th times 3 to the 16th. And I don't have to multiply all these numbers out and then find the remainder. I'm working mod 7. Well, I can say 2 times 4 is 8, and 8 is congruent to 1. And 1 times 4 is 4, and 4 times 2 is 8, which is congruent to 1, and 1 times 3 is congruent to 3. And so 3 to the 31st should be 3 more than a multiple of 7. Alright, and there you go. It's evenly divisible by 7. So instead of doing 3 times 2 is 6, times 4 is 24, times 2 is 48, times 4 is 168, or whatever it turns out to be, right? And then dividing that by 7, I can multiply these together and get 6. Multiply 6 by 4 is 24. That's 3 more than a multiple of 7. So this is congruent to 3. 3 times 2 is 6. 6 times 4 is 24. That's 3 more than 21. So this whole product's congruent to 3. So you can do this in pieces. And if you were going to do, a few million of these multiplications in a computer, you could do it and you'd never have a number bigger than, 6 times 6. And in fact, you could do it with, a simple multiplication table at your disposal for multiplying things modulo 7. So powerful techniques if you're doing things by hand, and useful techniques if you're teaching a computer how to do large arithmetic. And so when I was a kid, I was a math geek. I'm not now, of course, right? But I'm being laughed at. But I was a math geek, and I was really into prime numbers. And I learned that nobody had a formula for generating primes, and I was like, I'm going to find that formula, and I'm going to be famous, and I'll get a house with a pizza kitchen in it. And so I would come up with these crazy formulas that, I thought generated prime numbers. And mostly they just generated numbers where the first 3 or 4 were prime, and then after that they got too big to tell. But they looked prime. They didn't end with zeros, things like that. And I was reading a book by a professor named John Selfridge. He was at the University of Illinois. And I was like, I'm going to send him my prime number formula, and get famous. So I wrote him a letter. I think I was like 11 years old. I wrote him a letter, and I said, I believe I found a formula, and, here's the next number, but I don't know if it's prime or not. And he wrote me back this, like, big, long letter, and, said it was great that I was interested in math, and he was intrigued by my formula, and that unfortunately the number that I sent him is not prime, and it's divisible by, this 3-digit number. And he showed me how he did this with just a plain old adding machine. And he basically sent me this kind of calculations, and he worked modulo the divisor, and did really simple arithmetic operations, and was able to show that this number was congruent to 0 modulo this divisor. And it like blew my brain away, because I could not have conceived of how I could tell that, this 12-digit number was divisible by some other number, other than doing it by hand. And here he had done it with like almost no work. And that just seemed like magic to me. But that turns out to be something that, we teach our computers to do, because, we think of computers as like workhorses that can do all these big problems without effort, but they do take effort. And when you're trying to, raise a 500-digit number to a power that's itself, got a few hundred digits, that's a lot of work for a computer to do. And so we use these kinds of mechanics, modular exponentiation being one of them, and it makes it so that the computers can do these calculations quickly enough that things like, encrypting messages that we send out through a web browser are feasible, and we don't have to, wait around for a few days for the software to finish. All right, so that's the idea behind modular exponentiation, and we'll see some other tricks that relate to the idea of finding exponents quickly. And at the end of this, maybe next Wednesday, maybe the following Monday, we'll talk about RSA, a public key crypto system, and we'll use all of these techniques we're developing in a single glorious application, which is to come up with an encryption system that we can use for like e-commerce. All right, so let's keep talking about primes. So primes kicked in with this idea of if we make our multiplication table modulo n, if n is prime, we have a 1 in every row and column. If n is not prime, we have zeros in some rows and columns and no ones. So prime numbers tie into a lot of different things. They've been studied for at least thousands of years. I don't know how far back, certainly to the Greeks, probably to earlier Chinese history. And so definition of a prime number. So we have an integer, and it's got to be an integer bigger than 1. We don't talk about 1 being prime. We always start from 2. So n is prime if the only positive divisors are n and 1. So certainly every number is divisible by itself, and certainly every number is divisible by 1. But if those are the only positive numbers that divide n, then we say n is prime. Otherwise, n is composite. So what are the prime numbers? 2, 3, 5, 7, 11, 13, 17, 19, and so on. And you can tell that these are prime by looking for divisors. So you can pick a number like 17. It's divisible by 1. It's not divisible by 2, or 3, or 4, or 5, or 6, or anything up through and including 16. It's divisible by 17. So that makes it prime. But 15, for example, is divisible by 3, and it's also divisible by 5. So that's not prime. That's composite. So every positive integer bigger than 1 is either prime or composite. Like I say, 1 we don't talk about. 2 is a prime, but it's the only even prime number. Why is that the only even prime number?
Because every other even number is divisible by 2.
Exactly. Any other even number is going to have a divisor other than itself and 1, namely 2. But 2 sneaks in with that definition because it's divisible by 2, but 2 is itself. So it gets to be in the prime club. But no other even numbers.
It's to hang out with the cool kids.
Yeah, exactly. Similarly, any number that ends in 5 is not prime because it's divisible by 5, except for 5. Because 5 is itself. And similarly, any number that's divisible by 3 is not going to be prime, except for 3. Right? Because it falls into that, divisible by itself, that's okay. And so any multiple of any of these is automatically not going to be prime. Alright, so we can break our numbers into primes and composites.
Dragon keyboard?
It is.
Oh.
Yeah. All right, so every branch of mathematics has a fundamental theorem. There's the fundamental theorem of calculus. I don't remember what it is. It might be the one about definite integrals. There's fundamental theorems in all these different branches. There's a fundamental theorem of arithmetic. And so usually, you know, you want to pay attention to, like, what is this fundamental theorem? How did it get to be so important that it gets the title of fundamental theorem? So here's the fundamental theorem of arithmetic, and this might seem obvious. It very possibly will seem not very fundamental, but it turns out to be really, really powerful. And rather than write this out formally with a lot of flowery language, let me just tell you in plain English what the fundamental theorem says. It says if you take a positive number bigger than 1, you can break it down into a product of primes. So, you know, if you have some integer n, and it's bigger than 1, you can write n as a product of prime numbers. And more importantly, you can do this uniquely. And we'll put a little lawyer's asterisk on the word uniquely. You know, when you buy a product and it says, you know, guaranteed to make your clothes whiter, and there's a little asterisk next to it, that's the lawyer's asterisk. And it means if you read the fine print, it says may not actually make your clothes whiter. So uniquely, with a little disclaimer on it, and the disclaimer is, you know, up to reordering. Because, hey, you know, 15 is equal to 3 times 5. That's a product of primes. 15 is also equal to 5 times 3. Is that a different product of primes? No. We're going to say that these are the same because all we've done is rearrange the order of the prime numbers. So if we ignore, you know, rearranging the order of the numbers, this is a unique way that we can write every number bigger than 1. And if our number is prime, you know, 7 just equals 7, well, that's the unique representation of 7. But if you take 1001, that's 7 times 11 times 13. And that's the only way to write it as a product of primes, other than the obvious, you know, 11 times 7 times 13, or 13 times 11 times 7, and so on. But the only way we can write this as a product of primes is, you know, some ordering of 7 times 11 times 13. That's the fundamental theorem of arithmetic. So these primes are kind of the building blocks for all numbers. And the composite numbers are composed of prime numbers. So kind of like, you know, atoms and molecules, maybe. So the primes are like the atoms. Alright, this is sometimes called unique factorization. And it's unique factorization into primes. For example, I can also write 1001 as 77 times 13, but 77 is not prime. So that's not really a different representation of that. I have to break it down into prime numbers. And once I do that, it's unique. And this is true for the integers that we know and love and deal with on a daily basis. It's not true for all sets of objects, though. There are different number systems besides integers, and in some of those number systems we don't have unique factorization. And that's a startling surprise that ruined some people's days a few hundred years ago. But for plain old integers, we have unique factorization. Alright, I'm just going to keep going. We got 5 minutes left. Testing primality. So how do we tell if a number is prime or not? So you've done this in CSE121. How do you know if a number is prime?
You divide it by, or you modulo by like the square root of something or other.
Yeah, something like that. What would be an algorithm? You're on a desert island and there's a crate of food, but to open it you have to tell whether this number is prime. You don't have a computer, how would you tell?
Oh, without a computer, you're saying?
Yeah, just plain old, back of a coconut.
Back of a coconut.
Yeah.
Well, I mean, considering it's true or false, I'd probably be able to just guess, but...
Yeah, but if you guess wrong, the food disappears. It's magic food.
Probably still guess anyways out of laziness.
This is where I would pull out some SpongeBob money and offer it to somebody to, like, tell me whether a number is prime. But I can't do that through Zoom.
Do you, like, you go through each of the digits or something from the end? Or something like that?
Even simpler than that.
Zero idea, actually.
Even simpler. What's the brute force way to know if 147 is prime?
Divided by every single number underneath it.
Divided by every single number underneath it. Right? That's
underneath the square root of it, or whatever.
Yeah, so the definition is it's only divisible by itself and 1. So, try dividing by 2, try dividing by 3, try dividing by 4, try dividing by 146. Certainly, if it's not divisible by any of these, it's a prime number. And if it's not a prime number, it's divisible by at least one of these. And we'll find a divisor. So that's guaranteed to get you the right answer. And then, as you just said, we don't actually have to go all the way up to 146. We only have to go up to the square root of our number. Because if it's divisible by something larger than the square root, it's also divisible by something smaller than the square root. And so we would only have to go up to, about 13. And we don't have to try dividing by any even numbers other than 2. And so we really just need to check odd numbers up to and including the square root. And so that's usually the version that people write in CSE121. You make a loop, and you first you make sure it's not an even number, and you make sure it's not 2, because if it is, it's prime. And then you make a loop that starts at 3 and goes up to the square root of the number, and you just check to see if it's divisible by any of those factors. As soon as you find a divisor, you can immediately say it's not prime. But if you go all the way through the loop and you haven't found a divisor, then you say it is prime. So that's called trial division. And it's sort of the most straightforward way to test for primality. It's also about the most painful way. It takes the longest amount of time and it takes a lot of work because you got to do a lot of division. Division is hard. All right, so Monday we'll continue talking about this. We'll talk about other tests for primality, some facts and properties of prime numbers and of the set of prime numbers, including something called the prime number theorem. And then we'll talk about some open problems related to primes and number theory, and then we'll start talking about applications, and that'll lead us into crypto systems. So that's coming up next week. All right, have a good afternoon. I will see you next time in class here or in 222, and hope everybody has a good weekend if I don't see you before then.
Thank you.
Thanks.
That's it.
Have a good day.
Thanks, you too.
Quick question.
Yeah.